So if it's my unit of circle on a complex plane, then within the interior of that circle, including the boundary, in fact, there is no any solution at all of this polynomial. We cannot possibly, I'm not sure if you can find the solutions themselves, but we can easily establish that those solutions, there are solutions, we know by the fundamental theorem of algebra, there are solutions, but none of them will be within this circle. So formally speaking, we look at something like this. We have to see that if I have a complex number z with the property that it vanishes my polynomial, so if I have any root of my polynomial, then for such root, this root must be outside the circle. So we have to see this. We have to see this implication. The proof goes, there is a simple proof which relies on inequalities, triangle inequality and reverse triangle inequality, and it goes by contradiction. And we do it like this. I will do it like this. You might find some other ways to do that. We start with the number z, which is in fact opposite to what we have to conclude. The one which within this circle, it might be on the boundary. Now, what we do is this. We take my polynomial, and we take the absolute value of that polynomial, and we try to estimate that absolute value. Look how we're going to do that. Well, that's my polynomial with absolute value. Now, I use my triangle inequality. No, wait a second. I'm not using my triangle. I will modify this a little bit, this one, just a little bit. I'll do it like this. Look at this. I say free first, this free, and then I put negative, and then I put the remaining terms in brackets like this. Nothing has changed, in fact. Nothing has changed. But now I'm in a position to apply my reverse triangle inequality. This is number z, this is number w, this bracket, and we have a difference. So I can show this. Well, if you copy the inequality, look at that, you can see that we can do that. If I apply my reverse triangle inequality, it will be absolute value of 3, take the absolute value of negative z, take negative z4. Right. Negative value of 3, it's just 3. This one just like this. That's what we came, that's where we came. Now, for this one, I will use normal triangle inequality. Look at this. I say the sum of these two in absolute value doesn't exceed the sum of the absolute values. Each of these numbers, z and z, we assume this number to be less than 1 in absolute value, so this one, just 2. In fact, again, just 2. So look what happens here. For this difference, I replace now this absolute value with number 2, which by the consequence of this inequality, bigger. If you replace any difference, the second term with a bigger quantity, the difference becomes smaller. Everybody agrees with that? So I can put another bigger or equal inequality and replace this absolute value with 2. And this is a very simple thing, it's just 1. Look what we just established. We started off from the number z like this, and we showed that the absolute value of p of z bigger or equal than 1. In particular, it means it cannot possibly be 0. So we just established the opposite of this, the negative of this application. We took any number within a circle, and we realized that for such a number, this will be bigger than 1 in absolute value, so it cannot be 0. That's why there is no roots within this circle. That finishes this implication. I can kill this question mark.